Let's talk about using capacitors in circuits. And I want to make this conversation as generic as possible. A capacitor, again, the circuit symbol is like this, is an example of a two-terminal device. And that simply means that it has two wires that you use to connect it. Other examples of two-terminal devices would be a battery, which we talked about in the last video, a switch, a resistor, which we have not yet talked about, an inductor, again, we've not yet talked about those, a diode, we haven't talked about that, a lamp, like a light bulb, so for any of these devices, there are only two ways to connect two of them together, to connect two such devices. And it's important to understand these two ways because they form the basis of building up more complicated circuits. One way is called connecting them in parallel. So that connection is like this. I'm going to use an X to symbolize any one of these. So the X could be a capacitor or a battery or any of the other ones. So if they're connected in parallel, it's like this. So electrical current flows in on this wire. It divides up, not necessarily evenly, but it divides up. Some flows through this top arm, some flows through the bottom arm. It recombines here, and the same current flows out here. So these straight line segments are wires, and in the way that we are modeling the circuit, there is no voltage difference along a wire. So that means in particular that the voltage here is the same as the voltage here because they're connected by this wire. And similarly, the voltage here is the same as the voltage here. So that means the voltage across the top device, let's call the top device 1 and the bottom one 2, the voltage across the top one is the same as the voltage across the bottom one. So for parallel connections, V1 is equal to V2. The current, let's call this one I1 and I2, the current does not have to split evenly between them. So I1 need not equal I2. They could be equal, and they will be if the two devices are identical, but in general they don't have to be equal. A second way that we could connect them, the only other way, is in series. And in series, we just put them one after the other like this. Now the same current flows through both of them. So I1 is equal to I2, but the voltage drop, the voltage difference between the two terminals of the first device doesn't have to equal the voltage difference across the second device. So V1 need not equal V2 for a series connection. Let's apply these ideas to capacitors. So let's say if I have capacitors in parallel. Let's see if we can understand this in a deeper way. So the circuit would look like this. I've got two capacitors. They don't have to have the same value. Let's call the top one C1, the bottom one C2. When I flow charge in, I've got some current coming in, I've got current coming out. As I flow the charge in, it starts to build up on the left plates of both capacitors as a positive charge. I'm sucking positive charge out on the right side, so I'm building up negative charge on the the right plate of both capacitors. From the outside, if I sort of look at this as viewed from the outside, I've got a total charge that I put in on here that combines the two. So I could write that Q total is equal to the charge on the top plate of top capacitor plus the charge on the bottom capacitor. Again, I've flowed a certain amount of charge in it. Maybe it's split up. I don't really care about that in terms of viewing it from the outside. I just put in some charge, and that total amount got split between the two. Similarly, on the right side, the total would be negative Q total on the two right plates. Because the two capacitors are connected in parallel, we know that their voltages are equal. So V1 equals V2 equals V. So V1 is the voltage difference across C1, V2 is the voltage difference across C2. I can think of the combination of two capacitors as a single equivalent capacitor. So as viewed from outside the box, this looks like an equivalent capacitance. And remember, the definition of capacitance is charge, which in this case would be total charge, divided by the voltage. So that's Q1 divided by V plus Q2 over V. And we recognize Q1 over V, that's just C1. Q2 over V is C2. So for capacitors in series, the net capacitance is just the sum of the individual capacitances. I got confused. I meant to say for capacitors in parallel, the net capacitance is the sum of the individual capacitances. If I had more of them in parallel, like this, you can see it would just, the total charges would just add up in the same way. So it would just add plus C3, etc. So for capacitances in parallel, you simply add the capacitances. What about capacitances in series? Capacitors in series. This is slightly trickier, but still not too hard. So let's start with two capacitors in series. So that would be like this, C1 and C2. And we're going to start with them being uncharged. And again, I will flow some current in on the left, suck the same current out on the right. As I start to do that, I'm going to build up positive charge on this left plate and negative charge on the right plate. There is a central H-shaped area, see this H here, which is not connected to the rest of the world. So that has to remain electrically neutral. To minimize its energy, it's going to have charge flow over here, which is equal in magnitude to this positive charge. So some negative charge goes there, and some positive charge will go over here that's equal in magnitude to this negative charge. If it's not equal in magnitude, that would be a higher potential energy situation. Let's say that the charge on the left here is little q, and the charge on the right that is negative big Q. And I want to know, how does little q, the charge on this left capacitor, relate to the charge on the right capacitor?